Good morning. Happy Friday. Yeah. I hope you have a great weekend. Just a reminder that on Monday, we meet for lab at 1:10. You'll turn in the density lab that we did this week. Problem set number 2 will be up, and like before, we'll go over the problems on chalkboards and stuff before you turn it in after you self-correct. Quiz number 2, we'll have stuff from problem set number 2, and then we'll go next door and do the nomenclature lab. And again, nomenclature is just the way that chemists name compounds, so that's kind of what the idea is there. Questions on any of that? On Wednesday, we left off talking about the third part of periodic tables. All good periodic tables have at least 3 things on them. Some have more, but they'll always have 3. First of all, they'll have the symbol for the element. So for example, Be right there is beryllium, all right? Our periodic table that we're going to use has the name beryllium on it too, but at least periodic tables will have the symbol. They'll always have the atomic number, and if you remember, atomic number is the number of protons. So beryllium always has 4 protons. If you take away a proton, it's no longer beryllium, it becomes lithium, which has 3 protons. And if you were to add a proton to beryllium, it becomes B, boron. So that literally changes the element when you change the number of protons. But the last piece that it has on there is probably the most important. And right now, we're going to call it atomic weight. Now, it has different names, all right? We're going to call it molar mass in the whole class more than we'll call it atomic weight. And I'll talk about that here in a little bit too. What that number represents is that average mass of all the atoms together when you're using it. So remember how if you put like a little bit of water down the sink, that's more, if you put like a teaspoon of water in the sink, you just put more molecules of water down the sink than there are teaspoons of water in the Atlantic Ocean. You're going to get sick of me saying that, I'm sorry. We have a lot of atoms at any one sample. So boron, as we talked about on Wednesday, comes mostly as 2 isotopes. And we'll call them boron 10, which gets the little superscript in the upper left corner there, and boron 11. Now, those atomic numbers represent the protons plus the neutrons. So if this is boron 10, we can find quickly the number of protons by looking at the periodic table. 5 protons makes boron. Boron always has 5 protons. So if the mass number, which is what that number represents, is 10, the number of neutrons would be mass number minus atomic number, or in this case, 10 minus 5 neutrons. But boron also comes as boron 11. Now 11, mass number, minus 5, atomic number, equals the number of neutrons. That's going to be 6 neutrons, so a little heavier than boron 10. Okay, and again, I kind of think about that as flavors, but that's not really a good analogy because you don't want to be eating elements, that's for sure, usually. But the interesting thing is, all right, if I did a poll right now between vanilla and chocolate ice creams, all right, inevitably one would be more of a favorite. I'm guessing chocolate. I don't honestly know, and I'm not going to take the time to use it. Don't worry about it. Percentages are a big part of isotopes. So let's assume that this class likes chocolate more than vanilla. It's making me hungry now, but anyway. These percentages are how abundant the isotopes are, all right? So maybe 80% of the class likes chocolate and 20% likes vanilla. I don't know, something like that. Well, boron has percentages too. About 80% of boron is boron 11, and about 20% is boron 10. And that's important because if I had a big bag of boron atoms and I started pulling them out, all right, at random, all right? 2 out of 10, or 1 out of 5, of those atoms would be boron 10. And 8 out of 10, or 4 out of 5, would be boron 11. All right, so I've got a whole bunch of different kinds in there. So when you have that final number on the periodic table, it's an average of all the different isotopes and how abundant they are. So the boron value on the periodic table is 10.811 to lots of sig figs. And how they got that number is they took the mass number of the first isotope, which is roughly 10. That's what that 10 means right there. Most of the mass of the atom is in the protons and neutrons. Electrons don't have very much mass. The 10 goes right there, and it's 20% abundant in a decimal form. That would be 0.20. So it's the abundance, how often you have boron, times the mass, 0.20 times 10. And you add it to the abundance of the other one, which is 0.8 in decimal form, times its mass, 11. And that comes out to be 10.8. So all those numbers up there, all the red numbers on these periodic tables, all those red numbers are averages, all right? Back to my big bag of boron. I'll be pulling out boron 10s and borons 11s, but I'll never have a 10.8 boron, all right? Never going to be quite that number. It's analogous to, like in the United States, they say there's like 2.5 kids per family. And you will never go to a house and see like a half kid. That's disgusting, Halloween-ish. But anyway, you'll see families with 2 kids and 3 kids, or 1 kid and 4 kids, or 0 and 5, etc., etc. But you won't see like a half kid, all right? So 10.8 is like the half kid. You're not going to see a 10.8 boron, but you will see this if you're dealing with a bunch of them at the same time, which is what we do when we see all the families in the United States. You had a question.
Let's see, what does like isotope mean, like with the base? Is it like, you know how it's like Greek, like prefixes and stuff? Do you know what it means?
So an isotope means you have the same element, same number of protons, but the number of neutrons varies. So boron 10 has 5 neutrons, and boron 11 has 6 neutrons. And so this one would have more mass, be heavier than the other one?
No, I meant like the 3 chords, iso and tone. You know, never mind.
Okay, I'm not sure what you mean, but ask me after class and stuff. So yeah. For right now, what's important is that this number is the isotope number. It's protons plus neutrons, and you can always find the protons from the periodic table. Other questions? Okay, this number is going to be the most important to us of all time, what we're going to see here in a little bit. So let's say I wanted you to know the atomic weight of lithium. Well, one thing you could do is you could calculate it. You could take the 6, the mass number, times the decimal version of the percentage. So if you divide this by 100, that would be 0.075. Multiply that by 6, and add it to the decimal version of this, 0.925 times the mass number, all right? But you can also just look at the periodic table, which is cool. 6.941 is the atomic weight of lithium. So again, most of the time, roughly 9 out of 10 times, we would see lithium 7. About 1 out of 10 times, we'd see lithium 6. But we very rarely deal with individual atoms. We're mostly dealing with huge, huge numbers at one time. That's where that 6.941 comes from. You can do it for more than one isotope. Silicon has 3 main isotopes, all right? 92.23, 4.67, 3.10. Now, without looking at the periodic table, and if you do, it's okay, do you think the atomic weight of silicon, based on these percentages, will be closer to 30, 29, or 28? 28, well done. In math, if you have a higher percentage, you'll have more likelihood that number for your average. And so based on just these numbers, if more than 9 out of 10 percentage points are silicon 28, the atomic weight of silicon should be about 28. And if you look, sure enough, on there, 28.0855. So that's one way you can predict what the atomic weight's going to be. Also with lithium, 6.941 was the number up there. 6.941, if you rounded it up to 1 sig fig, would be 7. So sometimes you can make predictions as to which is the most abundant isotope too. Speaking of which, here's a question. We've got some random element E. And element E has 3 different percentages, and the question is, which one would be the most reasonable atomic weight? Well, because this is the highest one, we would expect the atomic weight to be close to 72, all right? Because more than half the time it's going to be 72. But if you look down here, here's 72.1, 72.8, et cetera, et cetera. Now, it is more than 50%, but it's close to 50%. And you have a pretty good percentage here of the higher isotope. So you could figure it out. You could take 72 times 0.545 plus 73 times 0.156 plus 74 times 0.299. But I would feel pretty confident claiming it's probably not that close to 72. It's going to be a little higher because we do have considerable amounts of both isotopes. So in this way, you can use either way you want, but 72.8 is a good guess here for which one's most abundant. If this would have been like 90% and these would have been 5% or something, then I would have said, yeah, probably 72.1. But anyway, probably it's going to be closer to that one. Any questions on that? Okay, nitrogen has two isotopes, nitrogen 14, which is very, very abundant, but not 100%, and nitrogen 15. And to calculate the average mass, what you would do is you would take the abundance, which is nothing more than the percent in decimal form. So take this number, divide by 100. Also take this number, which is already small, and divide by 100. And multiply those numbers by the masses. Now we have a lot more sig figs here, so we'll get better answers than we did before, but it's the same idea. So mathematically what it looks like, 0.996299 is this number in decimal times its mass plus this number divided by 100 is this times this mass, all the sig figs, 14.0068 AMUs. AMU is a really small amount of mass that's used for atoms. It stands for atomic mass units, sometimes called daltons. Very, very small. Now, a question for you. On this periodic table, it says 14.0067. Why do you think the periodic table is a little different than this calculation? A couple answers, yeah.
Significant figures?
Could be significant figures, you bet, using better ones. I like that.
They found different amounts depending on the current.
Absolutely. Different amounts, different percentages. Absolutely. Also, there's more than two isotopes. All right? There's 14 and 15, which dominate the dojo, but there is actually a nitrogen 17, if I remember, and a nitrogen 13. So all of these things play into effect. And that's why all those numbers on the periodic table, sig fig related, they're all determined by experiment. All right? So just be aware. The periodic table does change once in a while, and it's mostly the atomic weights because they get better values, better sig figs, better percentages and stuff like that. Cool. Now, this is a kind of a problem you might see. This is an example with gallium. And gallium has two main isotopes, gallium-69 and gallium-71. And there's the masses to lots of sig figs. The average atomic mass, which comes from the periodic table, and you can look at right there on number 31, 69.723. Calculate the percent abundance of each isotope. Now, this kind of problem is only for two isotopes. It doesn't work for three, as we'll talk about. But if you have two isotopes, you can actually solve this. If you've seen this before, you know how it works, but if you haven't, here's how this works. The average mass is what everything is equal to, 69.723. And we don't know the abundance of gallium-69, but we know its mass. We don't know the abundance of gallium-71, but we know its mass. So you can see here in this kind of problem, we have two unknowns. We have an x and a y. And in math, it's very difficult to solve equations with two unknowns, right? If you have one unknown, you can solve for that x. But two unknowns is a little crazier. So, in a problem like this, if you only have two isotopes, then both of them together should equal 100%. Or, because we're dealing with decimals when we deal with these kind of things, they're going to equal 1. So what you can do is let y, put x on the other side, if you will here. Y will equal 1 minus x. X is the abundance of the 69 isotope. Now y is going to equal 1 minus x. So if you see a problem like this is how you knock it out. X plus y, the abundance of the first one plus the abundance of the second one, have to equal 100%, which in this case is 1. So you'll let one of them equal 1 minus the other. Any questions on that? Okay, so here's the math. Here's what this ends up with. You have one equation for the y, you substitute in 1 minus x, which is a lot easier. So now you have one equation with one unknown x. And we're going to solve here for this x right here, the abundance of the 69. Now, in math, to solve this kind of problem, you use the distributive property, which means you take this number, multiply it by 1, which is just itself, and you also take this number and minus x, multiply it by minus x. So you're going to have two terms with x, and you're going to have two numbers. And you want to get all the numbers on one side, and you want to get all the x's on one side. You want to solve for x. So if it's 3x, you would divide by 3. If it's 0.571, you divide by 0.571, and you do it to both sides. If you do this, you get 0.6012 for x, which is the abundance, the amount of the gallium-69. And then 1 minus x, 1 minus this number, gives you the abundance of the other isotope. That would be 39.88%. When you get these two numbers, it's a really cool idea to check yourself and make sure that the numbers kind of make sense. This is a more abundant isotope, the 69, than the 71. So the average mass, which was this number, should be closer to 69 than it is to 71. And you can see that 69.7 is closer to 69 than it is to 71. So you can kind of check yourself here to make sure it's good. If your algebra is a little rusty, all right, try this problem over the weekend. I've given you the answers, all right? Make sure you can go from here to these two answers. It is just algebra. I know you all can do it, but if you haven't done it recently, and over the summer you didn't do algebra for fun, practice makes perfect. Questions? Okay. So, here's another example. Antimony has two main isotopes, 121 and 123. There's the percentages, there's their exact mass, the average mass, 121.760. And the question once again, will you ever have one atom of antimony with this mass, 121.760? And I see a lot of you shaking your heads. No, correct. That is an average mass, all right? It is not an individual mass. You're going to have antimony with this mass about 57% of the time, and you'll have atoms of antimony with this mass 42% of the time, roughly. All right? All those numbers on the periodic table are like the 2.5 kids, 1.5 kids. I looked it up in Oregon. Oregon apparently has 1.7 to 1.8 kids per family. All right, cool. Anyway, so that's a fake number. You're not going to have 0.7, 0.8 kids. Okay, I have a weird sense of humor. But anyway, those are all artificial numbers, all right? And that's what those red numbers are. But we're going to use them all the time because we have so many atoms that we're dealing with. Not like a billion, not even a billion. We're going to have huge numbers. We'll talk about that here in a little bit. Questions? Okay. Now,
magnesium metal burns. The product of the reaction has a greater mass than that of the original magnesium. John Dalton's atomic theory successfully explained this seemingly strange result.
If you've ever been on a wilderness survival course, sometimes they'll have a magnesium flare, and it's really, really bright. So if you're at night, you can see it from a long ways, or even during the day, it's so bright, it kind of kicks out. Scientists took the piece of magnesium, which is a cool little metal strip. You can basically put it on fire, and you end up with some kind of white ash. And they measured the magnesium before and the magnesium after, and they found that the ash was actually heavier than the mass that they started with. And they didn't understand what it is. Now we know that magnesium oxide is the ash. So the oxygen is added to the magnesium to give it extra grams. So chemists have always wondered how to figure out how much oxide is produced. How much MgO will you get? If you put in this much magnesium, how much magnesium oxide will you get out? So chemists need a way to count atoms. So how chemists count atoms is we have what's called a counting unit. And if you've ever gone to the store and bought eggs, which I would imagine everybody knows about, you don't usually go and buy 1 egg or 5 eggs, but usually you buy a dozen eggs. And probably everybody knows that a dozen is 12. And if your parental unit says, I want half a dozen, you know to buy 6 eggs. Or if they say, I want 2 dozen eggs, you know to get 24. And a dozen is very similar to what chemists use to count atoms. Only in chemistry, instead of a dozen, it's called a mole, all right? So a mole is similar to the idea of a dozen, all right? A dozen is always 12. Well, a mole has a value too. So if you can buy a dozen eggs, you could buy a mole of eggs, or a dozen roses for a mole of roses, blah, blah, blah. But in my world, the mole is just a really big number. And the mole was named after this guy. Ostwald was the one that figured out how it was. I'm not totally sure where the name the mole comes from. Chemists like to use pictures of little moles running around with beakers and stuff. But anyway, the mole is just a huge, huge number. So while a dozen is 12, and everybody can probably see that one, man, Avogadro's number, which is the number used for the mole, 6.022 times 10 to the 23rd. Now, you bet this is experimentally determined. It keeps changing all the time, but it's the latter digits that keep changing, not the first ones. So in Chem 221 through Chem 223, you've got to memorize 6.022 times 10 to the 23rd, because this is a number we're going to use over and over. And I want you to kind of think about how big that number is, because 10 to the 3rd is 1,000, and 10 to the 6th is 1,000,000. 10 to the 9th is 1 billion, so 10 to the 18th would be 1 billion billion. This is bigger than 1 billion billion atoms, all right? It's freaking large. In my G-rated class, that's the only word I can use. It's really, really large and stuff. And this is what chemists use, because the atoms are so small. Powers of 10 come in factor. In certain books, you'll see the mole listed as big N sub A. We won't use that a lot in this class, but that's another word. And Avogadro was the first person to predict that there was probably a number out there like this. He didn't calculate it, but he did predict that there was probably something like it. So you can have a mole of copper atoms, and that would be 6.022 times 10 to the 23rd copper atoms. And you can have a mole of carbon dioxide molecules. Molecules are when you mix the atoms together, 6.022 times 10 to the 23rd. You could also have a dozen molecules, but that's too small, right? Nobody can even hardly use that many. So Avogadro's number, pretty important. Yes?
Are we going to use the number with 4 significant figures as compared to the whole number?
Use the 4 sig fig value, yeah. I mean, if you wanted to go on and use 6.022, blah, 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 but just use 4. So, yeah. That being said, don't use just 6.0 times 10 to the 23rd. In my sig fig world, as you can see from the density lab, 4 sig figs at least would be the way to go. Excellent question, man. Other questions? Cool. So I would memorize it. You can put it on your note sheet, to use on quizzes and exams, whatever you want to do. But we will use this number a lot, and definitely use at least 4 sig figs. I recommend 4 sig figs. All right. So if I have a mole of pure carbon-12, 6.022 times 10 to the 23rd atoms. Now, here's an interesting thing. If you have 6.022 times 10 to the 23rd atoms of pure carbon-12, chemists have worked the periodic table so that it equals 12.00 grams of carbon. And this is really amazing. I don't know, I'm still so amazed that chemists can figure this out. But a mole of carbon-12, 6.022 times 10 to the 23rd, which is 12.00 grams. So if you have 12.00 grams of pure carbon-12, that's a mole. So 12.00 grams is called the molar mass, all right? It's the mass of a mole of carbon atoms. And what is just amazing is that by thinking about how all this works out, converting AMUs over and stuff like that, all the isotopes together, 12.011. And if you look at carbon on the periodic table, 12.0107, which would round up to 12.011, chemists have been able to coordinate the average mass of an atom of carbon with the molar mass. And this is just wild. Okay, so this is the number that pops up on the periodic table, but it has 2 meanings. It can mean the mass in grams of a mole of carbon. So if you have 6.022 times 10 to the 23rd atoms of carbon, it's going to have 12.01 grams of mass, which you can measure on the scale like we did this week in the density lab. On the other hand, if you're talking about the average mass of a carbon atom, it's also 12.01 AMUs. Most of the time, carbon is carbon-12. Most of them are 12.00 AMUs, but there's also some carbon-13, carbon-14, which makes it a little bit higher. So, big part of chemistry. Those red numbers, 2 meanings, all right? The mass of an individual atom of carbon, but statistically generated, blah, blah, blah. But really, more importantly for us, it's also the mass of a mole of the atom. So if you wanted to have in your hand 6.022 times 10 to the 23rd atoms of magnesium, you would want to use the molar mass. And the red number for magnesium, 24.31, round up. If you hold in your hand 24.31 grams, you have 6.022 times 10 to the 23rd. If I put in my hand about 18 grams of water, we're going to see that's the molar mass of water. My 18 grams of water, 6.022 times 10 to the 23rd molecules of water. So those red numbers, not just a little important, super important. They have 2 meanings, the average mass of an atom, or, which is more likely, the molar mass, the grams in a mole. So we can then start counting units. We can have 1 dozen of eggs and 1 dozen pieces of bacon for breakfast or something. Anyway, we can also do the same kind of thing for atoms, so we can control how much atoms are mixed with other atoms. And that's super, super cool. Cool. 4 sig figs is kind of how we're going to roll in this class most of the time. All right, that's why I loved your question. Molar mass will go out sometimes, like here on magnesium, tons of digits. If you can use 4 sig figs, so 24.31, honestly, that's fine most of the time. Once in a blue moon, we'll need more, but most of the time, 4 sig figs rocks our world. Questions? Getting kind of excited here, you can tell. So, woohoo! All right, so looking at the periodic table, all good periodic tables, like I said, have at least 3 things, sometimes more. Atomic number, number of protons, super cool to know. Symbol for the element, absolutely. So aluminum is Al, and Al is always aluminum. Just like 13 protons always means aluminum, and aluminum always has 13 protons. But probably the most important, as we'll see, is that final number. And it has 2 meanings. Atomic weight, if it's the mass average mass of an atom, or molar mass, how many grams you need to have a mole, which is that 6.022 times 10 to the 23rd number. Here's a question you might see. Let's say that you wanted to find the molar mass of the element with an atomic number of 12. So what you want to do is go to the periodic table. The atomic numbers are the blue numbers, the whole numbers. All right, atomic numbers will always be whole numbers. And if you look, atomic number 12 is magnesium. So if you look at magnesium, on the periodic table, like we just talked about, the final number, that red number, that's the atomic mass / molar mass. It's the 24.3050 number. This would be the molar mass for carbon. These are probably atomic numbers of protons. I think this is like titanium or something like that. Yeah.
So the answer for the molar mass of any element is that red number?
Yes, nice job. That's right. Yep, that's right. And again, you never, don't even think about memorizing. You'll get more familiar with it. Like I can splue off some of the elements pretty good, but I have to look at them too, and you can too, right? And that's why you can always have the periodic table in front of you. Bet. Cool question. 2 for 2. Other questions? Okay. So here are 1 mole amounts of some elements. Here's copper. How much copper is that, Dr. Vessel? Great question, student in the back. Copper, number 29 on the periodic table, that's 63.546 grams. All right, so somebody measured it out, like on the scales. That's how much that is. Here's sulfur. I think sulfur is what, like 32-ish grams and stuff, all right? Silicon would be about 28, et cetera, et cetera. Yeah.
See, what element has the most known isotopes?
The bigger the atomic number, the higher the number of isotopes. So when you get down to like uranium and bigger, some of those have a lot, would be my guess. I have a book in my office that lists all the known isotopes. It's from the 70s, so it's probably not super up to date, but it would give you an idea anyway. Some of them have like hundreds. So. Here's a more practical question. All right, we have 0.20 grams of magnesium, and we want to know how many atoms there are. Now, if you have a question like this, where you're going from mass in grams to atoms, you must go through the molar mass first, and that's the number, the red number you use from the periodic table, and then Avogadro's number will send you to the final answer. It is kind of cool to visualize. 0.2 grams would fit on your finger. All right, it's a really, 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 really small amount of magnesium. Pretty small. Okay, so 0.20 grams, let's first turn it into moles. Notice here I'm just using 4 sig figs because most of the time that's fine. This is a 3 sig fig number. You want to make sure that your molar mass doesn't limit the sig figs. So if you do this out, it comes out to be 8.23 times 10 to the minus 3 moles. Whoopie-doo. That doesn't mean anything to me even after all these years. It's just a number to get to where you want to go. But the more exciting thing is if you find the number of atoms. Because once you have the mole, every mole, 6.022 times 10 to the 23rd. And it doesn't matter if it's eggs, donuts, or magnesium atoms like we're dealing with, same number. So you multiply that number by Avogadro's, and goodness gracious, 4.96 times 10 to the 21st atoms of magnesium. Now remember, 10 to the 18th would be a billion, and this is 3 orders magnitude larger than that. So yeah, your little tiny piece of magnesium, incredible numbers. People have done calculations on how long it would take to count an Avogadro's number of things, and it would take lifetimes. But anyway, we don't need to worry about that. Just really large numbers. All right, nobody's counting the individual atoms because they're so big. So grams to moles, always the first step, using the molar mass in the periodic table. And then if it asks anything about atoms, that's when you use Avogadro's number, but you do have to start with the moles. You could do it all at one step, or you could do it stepwise like I did here. Either way is fine. Okay, got pure carbon 12, and I have 3.011 times 10 to the 23rd atoms. Now, one little hint about this problem. If you literally have pure carbon 12 and not normal carbon, then the mass is exactly 12 grams per mole. We have 3.011 times 10 to the 23rd atoms of pure carbon 12. Does anybody want to, what's the relationship between 3.011 times 10 to the 23rd and 6.022 times 10 to the 23rd?
That's half.
Half, that's right, half, that's right. This is half the atoms needed to get to Avogadro's number. This divided by Avogadro's number is 0.5, 1/2. So 1/2 of 12, we'll find out how many grams there are. You should have exactly 6.000 grams. Now this only works with pure carbon 12. All right, actual carbon is 12.011 because of all those other pesky isotopes that are there. But at least for carbon 12, yeah. Questions? Okay. These last things are just going to be more informational than anything, but it's about the periodic table. And Mendeleev, a Russian scientist, was the first one to kind of put the elements in some kind of orders that make sense. Now, initially, he did it based on the atomic weights, the masses that were known, and that was kind of cool. The neat thing about Mendeleev's periodic table is that he predicted several elements before they had been discovered. I think gallium was actually one of them. But then, after a while, scientists realized that organizing the periodic table around atomic numbers was better. So this is an example of the old version. You can see there's 1, 2, 3s, which we'll talk about here in a little bit. And again, it did work pretty well, but it is better than, it's not as good as having atomic numbers. Now, on the periodic table, we'll talk about periods. And on the periodic table, periods go from the left to the right. So period 1 has only hydrogen and helium. Period 2 is lithium through neon. 3, 4 is complete, etc., etc. We'll talk about rows in just a second. I want to point out here, though, the lanthanides and the actinides. See how by lanthanum there's a star and by actinum there's a double star. Lanthanides and actinides go in the middle. So if the lanthanides and actinides were there, it would split them out a lot wider. This fits nicely on a piece of 8.5 by 11 paper, all right? That's like the periodic table we're using that does that. But do realize that there's like a break in there, and people usually just put them down there to save space. Now, groups are also really important, absolutely. Groups go top to bottom. Groups are more important than periods, that's why I'm glad you brought that up. Groups will go hydrogen, lithium, sodium, etc. That's group 1A. Group 2A is right here. Now, there's different ways to represent the groups on the periodic table, and we're going to use the system that's used right here. 1A and 2A are on the left, and 3A starts over here by boron and goes over to 8A. And in the middle are the B groups, all right? And you will see periodic tables in different formats, but this is the one we're going to use. 1A and 2A on the left, 3A and 8A on the right. By the way, notice that hydrogen is both here and here. Traditionally, hydrogen is just right there, but there is a reason why sometimes hydrogen is there, and we'll talk about that more next week. But for right now, just realize that most of the time, you just see hydrogen there, but if you do see it there, there is a reason for it. There's also rejected elements in the periodic table. Solid gases, which of course is silly. These are owned by the Microsoft Corporation, stuff like that. These are just silly things and stuff. Okay. My jokes sometimes don't work out too well. Anyway, so on the periodic table, when we talk about it, there's different kind of names that you need to hear. First of all, if you're using our version of the periodic table, the A groups are on the far left and the far right of the periodic table. We're going to call them main group elements, and that's going to be important for what we'll talk about next week. The B groups in the middle, as well as those lanthanides and actinides that are under there, the lanthanides, actinides, those are all called transition metals. And we'll talk about why that's important. All of those are here, and also those two groups right down there. And then finally, there are also things called metals, nonmetals, and metalloids. Then the metalloids are kind of this green part right here, and it kind of separates the metals on the left, the nonmetals on the right, and these metalloids are kind of a mixture. So I want you just to hear these terms so you know. Now, hydrogen is over here. It is more of a nonmetal, but we're going to talk about why it does have some properties that could be considered metallic. So that's why they place it on the left. At the University of Oregon, they have a really cool display showing actual examples of a lot of the elements. And you'll see that a lot of them are missing because a lot of them are radioactive. They'll break down, stuff like that. But if you ever are at the U of O, it is a pretty cool kind of a display to show what's going on. Yeah.
Well, I've quite heard the metalloids. There's like a debate on like which one's a metalloid.
We will talk about the debate in a little bit. You bet. But the important part for right now is just to know that there is kind of a line, things on the left more metallic and things to the right more non-metallic. Cool. All right. All of the groups have names, and only four of the names would I like you to know. The other ones I just want to point up here. The four names I'd like you to know, 1A, those are called the alkali metals. Sodium, potassium, lithium, rubidium. These are pretty common. Those are group 1A. Alkaline earth metals are group 2A, right next door. Magnesium, calcium, beryllium, strontium, also very common. So alkali metals, group 1A, alkaline earth metals, group 2A. They sound really familiar. I am just the messenger. I did not make these names, but just realize that they are right next to each other and they are different. Now, on the far right are the noble gases. Helium, neon, argon, krypton, etc. Those gases are almost inert, and they used to be called the inert gases, but clever chemists started making compounds with them. Woo-hoo! So they lost the inert name, and now they're just called noble gases. And the halogens are in group 7A, which is right next door to the noble gases. The halogens are also really important. Chloride, bromide, iodide, fluoride, etc., etc. They're used a lot. So 1A and 2A and 7A and 8A are the important ones. I'm going to let you know that right now. Now, notice that these have 1s, 2s, 17s, 18s. There is an international version of the periodic table which lists the columns from 1 on the far left to 18 on the far right. So group 1 would be the alkali metals, group 18 would be the noble gas metals. There are uses for the international version, but it's not very useful for us in this class. So if you see it, it's totally fine. If you want to use it, I'll help you translate what I'll talk about into that. But overall, try to stay away from it just because it's a little confusing. Now, group 3A, which is right here, it's got aluminum, boron, gallium, these kind of things. The fancy name is icosagens. I'm going to call them the twisted metals, and I'll tell you why in future lectures why I call them twisted metals. These are not names you have to know, but if you do hear them, I want you to kind of remember, oh yeah, Russell said something about it, but I won't ask you questions and stuff. Group 4A is a very random group of things, but very useful. They're called the crystallogens. Group 5A, nitrogen, phosphorus, arsenic, pnictogens. Group 6A, which is oxygen, sulfur, selenium, tellurium, etc. Those are the chalcogens. So those are just kind of cool names to know. And if you're at a chemistry social party, you say, well, I'm studying the chalcogens right now. Really, I was just studying the pnictogens. It sounds impressive, but really it's not that cool. 1A, 2A, 7A, 8A, please know those names. But the other ones, just throwing them up there so that you can talk the talk. All right, so you'll see sometimes questions like this. What list of elements contain an alkali metal, a pnictogen, and a halogen? Now again, we won't spend a lot of time with this, but alkali metals, that's group 1A. Pnictogens would be group 5A, and halogens would be group 7A. This is a problem where having the periodic table is super handy. Punchline is that answer E has that. So rubidium is close to the end here of the group 1A, so that would be an alkali metal. Antimony, Sb, all right, is right there. It's in group 5A, so it's a pnictogen. And finally, astatine is kind of a wild radioactive element that I wouldn't recommend. Let's go uranium or lead underwear on. But anyway, it is technically a halogen. It's group 7A. So again, just a reminder, you never have to memorize the periodic table, but if you are more familiar, it makes these kind of problems easier, stuff like that. Any questions on that? Okay.
The engine of the NASA space shuttle is fueled by the elements oxygen and hydrogen. A huge amount of energy is required to lift the shuttle into orbit. When mixed and ignited, the fuels produce water and a large quantity of energy.
Cool. Hydrogen's the simplest, and you might think, oh, hydrogen's wussy. No way. Hydrogen's really cool. It got the space shuttle into orbit and stuff using a mixture of hydrogen and oxygen. It's what makes the sun warm, makes it glow on us, gives us life and stuff like that. Hydrogen is super, super important. Because it's so explosive, it has caused issues. The Hindenburg crash in 1939 was this big Zeppelin that caught into fire. Amazingly, not that many people were hurt even, which is crazy, but man, there was a lot of energy in hydrogen if you do it right. What's really cool to me as a metal person is that metallic hydrogen was predicted for a long time. Now, hydrogen technically is a non-metal, we'll see, but it's in a group with other metals. And so in theory, it can be metallic. We'll talk more about what it means to be a metal in the next section. But in January of 2017, some German scientists observed metallic hydrogen, and it had to be pressurized really heavy. They think that the center of Jupiter has metallic hydrogen. Who knows? But anyway, hydrogen can be a metal, but in our world, almost always it's more of a non-metal.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. Oh, thank you very much. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Whoa, that is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it. Oh yes, I like it already. Now what's that going to do when it hits the water? It reminds me of a depth charge in a bathtub. Fair enough, mate. I'll leave you to it. Good luck. Thank you. Okay, John, go for it.
Warning, extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. So there you go. Today's lesson:
Never mix alkali metals with water.
Now, that's what Brainiac thinks will happen. This is an actual video with the last two metals they showed.
Here's rubidium. Rubidium in water reacts much more violent than potassium. Rubidium again. So as we go down the alkali metals, they become more and more reactive. So now let's take a look at the next metal, cesium.
All right, so all of these metals are super reactive with water. Don't put them normally in that. That video made these two look super powerful. They are powerful, maybe not as powerful as they made it sound, but it's cool. There's only about 1 billion atoms of francium apparently in the whole Earth, so there's not too much of it. We'll do more of this on Monday. Have a wonderful weekend. Thank you for being here. Take it easy.